Hi everyone, my name is Roderick. I am E3's technical manager, and I'll be talking about our Resolve capacity expansion model today. So let's just dive right in to talk about our perspective on capacity expansion models. We think that models like Resolve and Plexos and all these other capacity expansion models can help planners make decisions about how to balance competing objectives. The job of a planner can be very difficult in trying to make decisions 10, 20, 30 years out. And they need to balance policy uncertainty, technology uncertainty, economics, and try to develop long-term plans that can inform procurement. When at the same time, there are so many different resources that are available to consider, as you can see on the right. So keeping in mind all of these different dimensions of the problem, the models can help us try to sort of rigorously assess the trade-offs between these different options and provide indicative results about which directions are most promising, highest value. Maybe there are certain resource locations that are extremely low cost, high resource potential that we want to be planning for unlocking. So, capacity expansion models can help inform proactive transmission system planning that sort of helps grow the transmission system alongside generation expansion. At the same time, the models, as useful as they are, sort of exist within existing planning proceedings. So, one of the things that we continue to think about is that, proceedings for transmission planning tend to be different than generation planning and policy planning. And trying to align across these different proceedings with different timelines can be very challenging. But models like capacity expansion models can help planners across these proceedings make sort of more consistent decisions. So moving on to E3's Resolve model, this is a model that we built over the last several years. It grew out of prior work that we did in California for a RPS calculator. The intention of the RPS calculator and thus Resolve is to sort of chart out what the future looks like to meet different policy objectives. These days, that's SB 100. In the past, that was like SB 350. And part of that question is, what does the generation portfolio of the future look like? And at the same time, the transmission system underneath that needs to also evolve to be able to support that significant resource build out. So, diving a little bit into the sort of math of it all, Resolve is a zonal capacity expansion optimization model that has some representation of hourly system operations, such hourly zonal load resource balance. And it's trying to minimize investments in operations over the net present value of, depending on what project we're talking about, 10, 20, 30 years, to develop those sort of long-run proactive portfolios that show what the future portfolios look like. And those portfolios are obviously subject to different planning constraints like RPS, emissions targets, resource adequacy needs. Resolve has evolved over the years to keep up with changes to the resource adequacy discussion. A lot of discussion is around how firm resources are and how to keep resources reliable through renewable lulls or seasonal energy needs. And that will continue to be an evolving topic. With these least cost generation plans, as you can see as an example on the right, you can imagine that there's hundreds of gigawatts of capacity that's coming online, and there are sort of subsequent planning processes that help inform how much the transmission system investment might be. And we'll talk more about that in the next section. Resolve has been used to support lots of different kinds of studies, long-term decarbonization studies, which are very high level, talking about sort of policy directions. Moving down a little bit in the granular to a little bit more granular, we have done several utility resource planning studies where we're providing these utility integrated resource planning plans. And then finally, the most granular that we're talking about here briefly are bid evaluation or asset valuation, turning those long-term resource plans into near-term procurement decisions. And so Resolve has been pretty flexible in assessing all these different kinds of studies and trying to connect between these long-term policy objectives all the way down to procurement. We like to think of models as living in an ecosystem. Capacity expansion models like Resolve have strengths and weaknesses. In capacity expansion's case, the focus is on building models that give us long-run optimized portfolios of resource and generation, transmission, et cetera, investments, subject to our policy goals. Given that focus on long-run horizons, we have to make trade-offs in other areas of the model, simplifying operations or aggregating different resources, and we do that. In this case, we do want to just briefly talk about production simulation models, which have the focus of being very granular in operational constraints, trying to precisely model the configuration of a CCGT or different operating reserve constraints. So in many of our projects, we connect Resolve to production simulation models. One of the ways we can do that is just rerunning Resolve, fixing the investment variables and sort of adding more granularity to that operational dimension of the model. Another way we've done that is transferring optimized portfolios from Resolve to production simulation models. That can be a difficult process to align different models, but typically we do want to have the ability to look more deeply at operations. At the same time, production simulation, that sort of more accurate modeling can help inform or benchmark the operations in Resolve. And a lot of times that does take the form of helping us adjust capacity factors, adding operational constraints, adding maybe adjusting different operating reserves, or until we get to a point where that simplified Resolve operation mimics more, is a better estimate of that more detailed production simulation. Similarly, another kind of model that we've integrated or paired with Resolve are resource adequacy models like E3's recap model, SERVM, GE, Mars. All of these models operate in similar ways to assess the reliability of the system over sort of long-run outage scenarios. We're trying to achieve that 0.1 loss of load expectation or other reliability metrics. Again, we want to transfer optimized portfolios to these RA models because the resource adequacy model is not concerned with investment so much as simulating the system over different outage conditions until we're sort of certain about how reliable the system turns out to be. And in the reverse, resource adequacy models help us inform the reliability constraints that we put in Resolve. So that historically has been planning reserve margins, total reliability need calculations, effective load carrying capability surfaces that all help Resolve make better investment decisions. Certain resources may be better at meeting the system's reliability needs than others, and we want Resolve to be able to know some of that information in a simplified way so that the investment portfolios that it produces are reliable. And that can be an iterative process because Resolve has to make some simplifications. The resource adequacy models are valuable because they are simulating hundreds, thousands of years of different outage conditions to be able to accurately pin down those reliability standards. And finally, the last kind of model, there are other kinds of models that we could talk about, but the last kind that we want to talk about here are power flow models. In the context of transmission planning, power flow models are very important. Again, Resolve can transfer optimized portfolios and set points, assuming that we've captured those set points in our operational modeling, and use those to sort of seed a power flow model. Power flow models are valuable because they are modeling extremely detailed power flow optimizations over lots of different contingency situations, which may uncover infeasible configurations or maybe resource plans that are not feasible. In the reverse, power flow models, that detailed power flow modeling can help inform resource potential limitations, transmission path ratings, transmission upgrades, ratings or upgrading costs, can help inform which ones we want to be looking at. And all of those can be incorporated into Resolve. And as with across all three of these different scenarios, the planners need to make some simplifications to take what can be really complex modeling outputs from the right-hand side of these slides into this big capacity expansion model that's trying to optimize over all of these different dimensions. But capacity expansion models like Resolve are designed to be flexible, somewhat flexible, and try to adapt to all these different competing constraints. So now let's turn our attention to some examples of different approaches to transmission planning with Resolve. We'll talk about Resolve in particular, but these approaches do apply to different models like Plexus, Aurora, GenX. So just diving right in, I think the simplest approach, one of the simpler approaches that we have done in the past is a cost adder approach. So you can imagine that rather than modeling detailed, transmission and distribution topology and the entire sort of power flow load balance of the system, we are modeling a high-level zone. So in California, we've historically modeled CAISO as one zone. So within that, you might have different resources and different resources after you can try to tell the model that after a certain point, resources become more expensive because they incur some kind of transmission upgrade to make that resource continue to be deliverable to loads. So that's like a very simple heuristic to capturing that sort of economic trade-off between continuing to build the same kind of resource out in the same location versus building out a diverse portfolio of resources. Option 2 is scenario analysis. I think we tend to favor this option when we don't know that much about resource costs or transmission costs. We can just do in and out scenarios and say, if this transmission path were upgraded by 200 megawatts, how much does that sort of relax the transmission constraint? How much is it worth in terms of operational cost savings, investment cost savings, policy, compliance savings? So you get sort of a value number rather than an investment decision that's being made. The weakness of this approach is that it does require good scenario analysis, and this is only sort of feasible on a limited basis. You can't really do the scenario approach by hand for dozens or hundreds of transmission projects all at the same time. And finally, there is co-optimization. So this is where we're feeding the model transmission costs, transmission upgrade potentials, generation costs, generation potentials, and letting the model endogenously decide what that trade-off looks like. And that has the benefit of being able to capture all of those things on a seemingly level playing field, assuming those assumptions are reliable. Obviously, the weakness is that transmission upgrades can be very expensive and tend to be quite difficult and require long-run planning. From a modeling perspective, it can be difficult to model those transmission upgrades. You might want to consider integer upgrades so that you get these lumpy decisions. And you might want to consider them as like these long lead time investments that need to be made far ahead of the resources that end up being built in combination with them. So moving on to a case study, I wanted to briefly talk about how we've used Resolve to support the CPUC, California Public Utility Commission's integrated resource planning process and CAISO's transmission planning process. So these processes in California are connected. For the IRP, the CPUC uses Resolve in that sort of cost adder approach that I talked about earlier. So the CAISO gives the IRP input information about different resource zones and the transmission upgrades that are associated with being able to deliver more resources out of those zones than is available on the existing transmission system. So, there are resources, for example, in the Southern California desert, solar, maybe some wind, batteries, geothermal, and after a certain point, the existing transmission system cannot deliver more resources in that zone unless you start investing in transmission upgrades. So that's like a relatively simple representation of that sort of generation and transmission planning process that would happen in real life in Resolve. So Resolve has these cost adders that are applied to different resource groups in California. And out of Resolve comes those optimized portfolios. Moving on from step 1 to step 2, those zonal portfolios are mapped to different bus bars in CAISO system to start that transmission planning process. So the different agencies work on disaggregating those zonal portfolios into specific locations across the state. And the CAISO reviews that, analyzes that, and identifies different transmission investments that need to be made to support that large-scale resource build-out over the next 10 years or so. That's sort of very quickly one loop through the cycle, and as the generation and transmission plans are made from one cycle, they sort of feed in as inputs to the next cycle, and the idea is that the agencies are coordinating these different investment proceedings and decisions together through this modeling framework. I just wanted to briefly show this map because it sort of shows that even though from an operational perspective, we're modeling CAISO as one zone, that busbar mapping process, the sort of iterative process between IRP and TPP can result in this relatively disaggregated resource portfolio that has resources that are spread out across California and its neighboring states. You can see and this sort of achieves the goal of diversifying the resource portfolio, spreading it out so that not all of the development's happening in one location, and we're getting different kinds of resources that are being developed. Moving on to distribution versus bulk system planning, I think, one of the things that will continue to be a focus over the next few years is trying to assess the value of DERs versus bulk scale resources. And to start the discussion, we have sort of a cartoon of the entire system along the bottom of the slide. So, I think we're all familiar that there are, historically, we've thought a lot about generation or resource investments being at the bulk grid level. The previous section, we talked about bulk grid generation and transmission. We were sort of talking about that implicitly. And those are needed because those bulk grid resources need to be delivered to customers who are, down in the distribution system or to the right in this figure. So, our planning models need to be able to capture these costs that go from upstream down to downstream. However, there are these distributed resources that are out there, DGPV, efficiency measures, electrification, all of these things are also part of the system that we're planning for and have different effects on the system. So, the benefit of distributed resources is that they're close to load. They might not be subject to those transmission upgrades that are needed for bulk grid resources. However, the challenge so one thing we can do is model them all at the same time. We can model these DERs as options that utilities or regulators can try to deploy. The challenge is that distributed resources are subject to customer economics. A homeowner may want to buy DGPV for a different reason than the statewide regulator might. There might be reasons that they do or do not participate in demand response programs, et cetera. So, keeping all of this in mind, the realities of these different resources across the system, the challenge that capacity expansion models have is that, there are lots of investment decisions and upgrades that could be deferred, generation, transmission, distribution, customer-sided resources. And trying to balance all of these can be very difficult. But if we can unlock it, there might be locations where distributed resources are very valuable and very easy to deploy, in which case we do want our capacity expansion models to clearly select them as part of the portfolio. So as before, we'll talk about a couple of different approaches that we've taken to valuing distributed versus bulk grid resources. We talked about this for transmission planning, but it's worth reiterating that scenario analysis is always an easy and straightforward way of valuing resources or decisions. So that's just a simple in-out scenario, cleanly values the potential of one trajectory of DERs versus another without necessarily needing reliable cost data. A second more sort of analytically complex approach is developing avoided costs. So the goal is not necessarily to just have different one or two scenarios that show us different trajectories, but produce price signals that incentivize the right kinds of DERs to be aligned with system needs. And you can see that in proceedings like the CPUC's avoided cost calculator and integrated DER proceedings, which are trying to take CPUC IRP resolved portfolios, do some additional post-processing modeling to develop these hourly and annual value streams. The strength of this approach, or the reason that folks have taken this approach in the past, is that it allows DER stakeholders to evaluate the benefits of their resource or resource portfolios, customers, customer programs, without needing to rerun those system-wide portfolio models like Resolve or ServM, Plexus, etc. The goal is to agree on a set of value streams and say that these DERs can be evaluated. All the different combinations of DERs can be evaluated relatively straightforwardly. The challenge is that deriving these avoided costs can be quite difficult. Avoided costs assume that these DERs are affecting the system on the margin, and I think if planners think that DERs are going to be a relatively large part of the system portfolio in the future, that marginal assumption can be may not be true, and you might want to consider just a different approach so that you can better capture those interactive effects, those inframarginal effects. So that leads us to the last approach, co-optimization. And again, in Resolve, we've typically erred on sort of higher level zonal aggregations. So if you think of our example of CAISO being one operational zone, how do we model locationally specific distributed resources? And one way we've done that is to essentially develop price tranches, different cost tranches for different DERs. So you can imagine that there's some total potential of DGPV in CAISO in California. But there are certain pockets in the Southern California Edison system that have extremely high distribution system deferral value or other locationally specific values that make building distributed resources in that location really important or high value, versus somewhere else in the system where maybe investing in building a distributed resource would require upgrades to the system, in which case those resources are more expensive than that sort of baseline DGPV resource. So we've used that approach to try to split the difference between not needing to model all of the transmission and distribution topology, but still get that locational variation across the state, across the regions that we've modeled. One of the challenges with that approach is that while we can develop these sort of price tiers or supply curves of these DGPV DER resources, it can be hard to actually unlock those values. As we mentioned earlier, customers may not actually want to deploy these DERs where they're most valuable. And these are the sort of the approaches that we've taken in the past to value DERs and bulk scale resources. So just to summarize, this DER versus bulk grid analysis discussion, models like Resolve, even relatively aggregated models can help planners make decisions about DERs. We do just want to sort of caution that while the models can capture these economic differences if we parameterize them correctly, there are different proceedings, different incentives, customer versus utility, that drive the actual decisions that are being made. While modeling has advanced significantly in the last decade, we do need to understand that models need to make trade-offs. We can have more bulk scale. They need to make trade-offs between modeling more resource types, more resource tranches, more temporal resolution. There are lots of different dimensions of the problem that you could add accuracy to. And maybe DERs are the right dimension to be adding accuracy to, but they are being balanced with operational modeling, reliability modeling. These are all things that compete for the time and computing resources. Outside of the modeling itself, utilities are starting to understand that DERs are not are going to be a larger part of the portfolio. So I think something we're looking forward to seeing is utilities like Salt River Project, Hawaiian Electric Company, Duke, sort of align their planning processes so that we can get the inputs and the sort of stakeholdering aligned, so that we can sort of develop processes, modeling inputs, so that models like Resolve and other capacity expansion models can sort of fairly evaluate these different kinds of resources at the same time. With that, thank you for your time. You can see my contact information as well as Arnie Olson's contact information below.